Okay. So basically, what you can graph, we did go into functions a little bit, but if you were to sketch a graph of this function using Desmos, you would get a normal curve. This B is actually a number. It's actually the mean. B turns out to be the mean. Yeah? What was that? Okay. B turns out to be the mean. The A here, that turns out to be the standard deviation. So if you were to graph this for a certain value of B and for a positive value of A, not non-negative, it should be positive. Let me fix that. Then you would actually get the normal distribution curve. Mean would be B and A would be the standard deviation. Also, this EXP, that's just fancy notation for e to the x. That's all. Mostly because the exponent here, as you can see, has a lot of stuff in it. So what people use instead as notation is this, EXP of x. That's all. So if you do EXP of something, that's e raised to that. That's all. And before I show you how to graph it in Desmos, let me just say this. The notation I'm using here for B and A, I mean, it's really not too common. What people generally do is they like to use the Greek letter. This letter here looks like a U, but it has a tail on it. It's called mu. It's actually pronounced as mu. That's what I'm trying to show you by this, in quotes, mu. But that's the Greek letter, and people usually use this for the mean here. Although I just thought it'd be easier for everyone if I did A and B, but mu is actually what people use for the mean. Just notation. And this Greek letter here looks like an O, excuse me, a 0, but it has a little tail on top. This is actually sigma. Sigma. That's notation people use for the standard deviation. That's all. It's just notation people generally use. So instead of B and A, people generally would have mu and sigma instead. Okay. All right, let me show you in Desmos how to get these graphs. Let me just get it in Desmos, load it up. I mean, there was a website I actually found, and it gives us this stuff in Desmos. Let me show you. Here we go. But that website will actually take you to this stuff. And you can see that you can actually graph the normal distribution curve, as you can see, for different values of B and A. Keep in mind, A is the standard deviation, so A is positive, and B could be any number you want. But let me just, is that a mistake in my notes? Oh, there is a mistake. Let me just fix something, well, it shouldn't take that long. That's squared, this should be squared. The A here should be squared. Sorry about that. Let me just fix that real quickly. There we go. All right. I mean, there, as you can see, using E, I just thought EXP would be better because, at least now you get to see it. The A here in the bottom I have, on my notes should be squared. So I just fix that real quickly. Okay. I don't know, okay, can I see? Yeah, oh, they can see it. So I just had to fix it. So basically, this is what you get. And you can let A and B vary. And you'll see like what effect it has on the graph. For instance, let me show you. If I were to change B, right, which is the mean, you can see the graph is going to shift horizontally. Okay? You can see the graph looks kind of like a hill, right? The peak, the top of the hill, that is over the mean directly. So if you change the mean, you change the way where the graph is, you're shifting it horizontally. Whereas with the standard deviation, A, you can see how this will have a different effect on it. So if I want to graph a normal distribution curve with mean 5 and standard deviation 2, so I have this B set at 5, A set at 2, and we get it. As you can see. So this is what we get here. Okay. I even drew that. I even put this graph in the notes because, again, I did email you the notes, so it's in there. Okay. Now, let's actually see what changing the standard deviation does, like what effect that will have. Okay. So let's take a look at this. So if I were to fix B, say it's 0, let's do that. Okay, just to make it consistent. Well, if I make A bigger, which is the standard deviation, you can see that the graph is getting flatter, right? The peak is getting smaller, and the graph is becoming flatter and flatter. Mostly because the data values are going to be spread out more and less clustered around if you increase the standard deviation. Okay, so again, if you increase standard deviation, right, what happens is the data values are going to be more spread out. Standard deviation, as we saw, measures how spread out the data is. Okay. Now, if I made it closer to 0, then it's going to cluster around the mean. See, and you can see the graph will look more and more like this. The peak will get higher, as you can see. Okay. And the data centers more around the mean, and the median, I guess, in this case. So that's what happens if the standard deviation gets smaller. Okay? I will post a link to, well, the link I put in the notes anyway, to this Desmos thing. Although when you go to it, you're not going to see my name here because I guess someone made it public. So, but you can play around with this and see like what the different normal distribution curves look like. I mean, originally I was going to try drawing it by hand, but I figured it wasn't necessary because we have Desmos. So, I mean, in class, I would probably have you guys draw it by hand, but since we're online, I just don't see the point in that. All right, let's get back to the notes. Yeah. Are there any questions on this? All right, let me get back to the notes. There we go. Okay. Excuse me. So we saw what happens if we vary. So we saw what happens now if we let the mean and the standard deviation vary. Okay, that's cool. That's fun. All right, so I hope I'm not going too fast with this. I don't think I am. Let me show this though. But again, this is the graph that you would get if the mean is 5 and the standard deviation were 2. All right. Okay. So let's, I guess, might as well keep going then. All right. All right. Okay, so for the next result is actually what we call the empirical rule. This allows us to see where, most of the data basically lays, where most of the data is in a normal distribution curve. It turns out that if you're at the mean, let's say, right, and you go one standard deviation away, 68% of the data values will fall within one standard deviation. 68% of them will. Whereas, if you go out 2 standard deviations, about 95% of the data values will be. This is kind of going along with what I said earlier, that the further away you get a data value is from the mean, the less likely it's going to occur, the less frequent it will occur. And this is saying that within 3 standard deviations of the mean is most of the data going to be. Most of the data. In fact, let me show you the pictures that illustrate that. That is the pictures from, what do you call it, the textbook. Now the textbook, again, you could download for free. So let me just open that up. Here we go. As you can see here, right, in top, 68% of the data is within 1 standard deviation. Sigma here, they have this notation. That's a standard deviation, okay? If you go out 2 standard deviations, 95% of the data will be there, as you can see, and 97% will be within 3 standard deviations. So that's good. That's what we see here. All right? So that is what we see. Okay. Okay, so I figured now it'd be good to, yeah, let me see what's that. If I remember, I know I got to, this is where I got up to with the other class. So, but let me keep going though. But again, these pictures are in the textbook, so you don't have to copy these down. I think. Yeah, here we go. All right, so let's move on to the next slide, but let me get the notes back up. So this would be an application with that theorem, with the empirical rule. That's what it is. It's not really, I guess it is technically a theorem, but we call it the empirical rule. Okay. So basically, let's suppose I gave an exam, okay, in another class. Oh, boy. Excuse me. So let's say I gave an exam in another class. The exam was out of 15. And let's say